So, talking about calibration, the way I'd like to go about this is giving you folks an idea of what we're trying to achieve, or what I try to achieve, when I calibrate a display, whether that's an LCD, a plasma, an OLED, or a projection, and some of the methodologies, the tools that I use, and the things to look out for. I'm not going to run a program, I'm just going to show you some slides, and starting with this right at the moment, the idea is when you're calibrating is you want your display to accurately show you your data, and your data being your pictures. You don't want the pictures to look good if your data is not good. One of the end results of this is that your data can leave your facility and go to another calibrated facility and look the same, given a fairly similar viewing environment. And viewing environment is a very, very important part of this puzzle. We are inherently analog devices, our eyes. We make adjustments to light. We have irises. And we tend to view things relative to other things. So if you're in a room that has a lot of red walls, etc. like that, and you're trying to project a picture, I basically, if you want me to calibrate it, you're going to have to change your walls, because I cannot calibrate a reflective screen when the room is red. It just, I can't get the reds out of the screen. So that's the idea, is you want to get your device to match to a standard, and it has to be an accurate representation of your data. It's a combination of many things, actually, calibration. It's not a magic button. I know that there are automatic features in some of the calibration applications out there, but they're all accumulative things. And like I say in the last line here, everything affects everything. So when I've gone through an alignment calibration, I actually have to go back to the beginning and then check again, because my last step may have changed something else along the way. And you have to, like the middle line here is, I'm making compromises because I have never yet seen a perfect display. I don't think I'll ever see a perfect display. I'll be showing my age to say the closest I ever saw it was CRTs, but they had 40 years to get it right. The display technology we're seeing today is 6 months old, you know, and the display technology I'm seeing in a lot of the facilities, the vast majority of it is not professional broadcast equipment. It's prosumer at best, consumer, and in many cases, people are actually color correcting on basically a PC monitor. That's pretty scary stuff, but there are tools available to a calibrator to make a LCD monitor or a PC monitor look very good. But it's not actually the monitor itself, and I'll get into that you calibrate, because there's so little controls there. I'm getting ahead of myself and all over the place. So. Bottom line is, it's a whole lot of small improvements, and everything affects everything. You got to keep that in mind. So the results are going to be, we want to be able to see everything in the dark and everything in the bright area without any clipping, without any crushing. So somebody with a black shirt, you should still be able to see the texture of the shirt. You should be able to see stitching on it. If he's got a white shirt, it should be the same thing. If it's just a flat, there's no detail, same thing with clouds. If clouds just look flat, like an outline, you're losing data. And if data is important to you, you want to be able to see your data. You want to be able to know whether or not the camera clipped it. You want to know that if it's your display that's clipping it. So many of the displays of the consumers actually do clipping right inside, and it's very, very difficult to open that display up to show the full range. You want to match the video environment, something I mentioned before. I'll talk to the client and find out, show me how you usually sit in the room. What's the lighting like in the room? Where's the guy that's paying the money? Where's the guy that's paying the money sit? Where's the money seat? And most of the guys would be, if it's in a theater, it's right around the center, right? That's actually where you want to calibrate to. If it's in a smaller room, it's usually in front of the colorist. But it's important to take into account the environment, and sometimes you have to do two calibrations. One for a dark room and one for when they open up the lights. Open up the windows, perhaps, let's say, you know. You want to produce a full range of colors, and they should be accurate colors as well. And that is a very, very, very tricky step or process. It's very, very involved. The fact remains that you cannot correct for every value in even an 8-bit system, because the time it takes to do that the time it takes to profile. Your display has been on so long, your probe has been on the display so long, I'm talking weeks, that is where you started is not even there anymore. You want to minimize artifacts. A lot of these TVs that you buy have got, I call them customer features, but they're a nightmare for a colorist or a color corrector, calibrator to work with. You have to get rid of all of these auto ambient lighting adjustments, the active backlighting where they try to turn the backlights down to crush the blacks down a little bit more. Some of them have got noise reduction that's cranked way high. Some of them have got they've got a million different names for different things. You want to turn all of those off so that you can actually calibrate the display without interference from something else. Artifacting in the high frequency, if you put up the zone plate on a consumer TV, I don't know if you know what the zone plate is, but it will show you so many artifacts. Another one is multiverse. Put up multiverse and see if you can see the high frequency without banding or grouping or buzzing and things like this. There's this thing called mosquito noise. Turn that off. Okay, let's keep going. Am I going too fast? Am I no, too slow? I'm the only guy here tonight, so I'll go slow. Here are the things that you're going to have to look at and adjust to calibrate a display. Grayscale tracking. I'm going to assume everybody knows what these values are. If you don't know what these are, please ask me and I'll give you an explanation on it. Luminance, saturation, hue, uniformity, dynamic range, brightness and contrast. I put a star beside that for a reason. Gamut, gamma, those are often confused. And your white point, that is also a moving target. And image size, focus, and linearity. The gamma and the brightness contrast controls, they are greatly affected by the viewing environment. And they are a control, not so much gamma, but brightness certainly. It's something that a consumer can make small adjustments on if he turns all the lights off and he likes the way his display looks. And he turns lights back on again. He may want to bring the brightness up a little bit. And again, that's because of our eyes. Our iris down and the blacks will crush out. So he may want to bring that up. And that's actually okay within reason. A half-decent display will track and it's not going to go wonky. But the viewing environment is stressed again, is a very, very important factor in a successful calibration. You can't actually allow that to affect your calibration itself. The tools, that's all off to the side there. Tools, this is a base minimum of tools. Tri-stimulus photometer, a spectrometer, pattern generator, analysis software, and you're going to need to have miscellaneous adapters and whatnot to go with the various input interfaces. There's lots of choices out there for these things. You can spend a lot or you can spend a little. If calibration is important to you, don't spend a little because you're not going to get anything that's valuable. Brief explanation of what a photometer is or tri-stimulus photometer is. You have a light source that goes through RGB filters. Inside that device are 3 photo-optic cells which will tell you how much light came through the red, green, or the blue filter, and it just gives you an output reading of that intensity. These are quite cheap. They're very fast at taking readings, and they're not overly stable, because what happens is those gels, first off, depending on how much you pay for them, may not be terribly accurate. There's crosstalk in all of those gels as well, and they age. And one of the things that ages them is, first off, using them. Punching that light through it will bleach the gel. But also, heat. Heat will also affect those. And so after about a year or so, you should, even if it's a $250 photometer, it needs to be recalibrated if you're using it on a fairly regular basis. Otherwise, you're going to drift off. But as I say, they are inexpensive, and they do have a use. I use my photometer every day on every calibration, almost every calibration. And I'll tell you how I use it and how I maintain the accuracy of it. A spectrometer is a far more expensive device, but they don't have to break the bank. You can get them from anywhere about $1,000 up to $25,000. I use one that's $1,000 because I'm not building displays. I don't need something that's accurate to 1 or 2 nanometers. I need something that's more accurate than my eye and your eye, and probably more accurate than the display is capable of. Anyway, the way it works is it actually just looks at wavelengths. That's what the spectrometer is doing. It doesn't, it's not caring about how much light there is, or it's just how much did I see of blue, how much did I see of red, how much did I see of green within a frequency range. So the way I use my photometer is with my software. I will put my spectrometer and my photometer side by side on the display, and I will tell my application to, well, I've got my test generator connected, right? It creates a bunch of test patterns on the display, and it reads both probes simultaneously. And it will compare what the spectrometer tells me it got in wavelengths with what the photometer says it saw. And it will make a correction to the photometer. It will make a correction LUT or matrix. So that now when I read with my photometer, it tells me what the spectrometer would read if I used it. And the reason I use that is because in the blacks, it can take over a minute to take a single black reading with a spectrometer. But I can get it in a couple of seconds with a photometer, as long as it's properly calibrated. And a spectrometer has one other kind of a limitation, is that you have to do a calibration on it before you even use it. It comes with a National Research Council slab of ceramic white that you have to read against it, and that's the baseline for the spectrometer. But that only lasts a certain period of time before I'm forced by my software to recalibrate my spectrometer. So it stays very, very accurate, but at this point in time, the one I've got only runs for 240 minutes, which sounds like a long time, but not if you're trying to do a profile, which we'll talk about later on. Pattern generators, there's lots of selection out there. I think somebody mentioned that they have a DVD. There's DVDs that you can buy. You want to verify that your DVD player is correct. It's a good idea. Some of them have output controls on them that may have been tweaked. They may have a cheap chip. Let me try that. Cheap chip set in it, which will be altering the data. So your DVD disc pattern may be fine. It may be a solid 255, 255, 255 weight, but your DVD player may not be putting that out. There may be some analog jiggery-pokery in there, and you got to watch that. It has to have multiple frame sizes. It has to have multiple color standards, unless you're, well, I guess you could stick with 709 or 2020, if only one, but as a calibrator, I've got to do a lot of different ones. Interfaces to various displays, whether it's 3G displays, it's HDMI displays, there's a few DVIs out there still, you know, SDI, of course. And it should interact with the software, and by that I mean it's really nice if your software, your analyzing software, can drive the pattern generator automatically and run a macro, essentially, a series of tests, so that you don't have to go to your test generator, go next test, go back, take a reading, next test. You want to just wait, tell it to take a reading, and you got the reading, tell it to move to the next test. And that's very, very handy when you're doing a projector and you're sitting like about the fourth row back, and your test generator is back with the projections. You don't want to have to get up over there and push it up to the back. So you'll have an interconnect between the two, and it steps along automatically. And static and moving pictures are kind of an important thing to have in your test generator as well. 1 second. Then there comes the software. This is where the rubber hits the road, really. Your software makes sense of what your probes are sending to you. And it's really nice, I think Reed mentioned being able to talk to the devices. That's the DDC. Some of the software has the drivers built in. I know that Panasonic is in CalMan, so is the Samsung new QLEDs. A lot of display drivers are built into the CalMan Ultimate software, which allows me to also talk directly through my software to the display that's under test. And that helps you because, you know, some of these big panel displays, if a lot of places that I go to, they've lost the remote because it's up on a wall somewhere, they've lost the remote. And so I've got to go over to this thing and put my hands up behind it, trying to find the button and go through menus and try to make adjustments. That's relentlessly punishing and arduously painful. So if you have the DDC capabilities, or you can connect directly to that display device, then on my software, using a mouse, I can actually control the display. And if I go into an AutoCal situation, I can actually let the software take the reading, move to the next generation, the next pattern, take a reading, and make the adjustments as it goes along. I give some time to get some coffee. The spectrometer, photometer matching, that is something that my software does, and that's the thing I talked about earlier. You want to make sure that you can do that. If you have got if you only have a photometer and you've got a number of displays, you probably can make all those displays look very similar using that photometer. They probably all will have an error in some direction, but they'll all be pretty much the same error. So you'll be happy in your facility, and hopefully it won't be so bad that if you're down to go someplace else, you get caught with that pointing fingers. Well, it looked better there, and it looked there with your display, whatever. So it's kind of a nice thing that if you can, doing calibrations, especially if you're a calibrator like I am, where I go around to a lot of different facilities, that I can provide them with a report that shows the performance of their display, that they can look back at, and they can say, okay, that display did have a little bump in green at about 30 IRE units, and that's what we're seeing because of this particular data. You can do the best job you can on a calibration, but as I said, I've never seen a perfect calibration. And so you've got these tiny little errors that you try to minimize. And that's why when you've got an AutoCal, it's really important to have manual overrides, because the artificial intelligence is going to make a decision on where it thinks it should be. And it's going to be looking at the RGB values, and it's going to be looking at the absolute white values, if it's matching gamma. And it's going to make a decision. What you never want to do is have a plus green error. If you can avoid it, always avoid it. It's much better to have a plus blue or a plus red error than a plus green error. That's because our eyes are far, far more sensitive to green than it is to the other primary colors. And a very small green error will show up where that same error in red or blue, you wouldn't detect it. So that's when you come into the manual overrides, and you can see it's it's boosted the green a little bit perhaps because it wants to get the luminance up. Well, you might be better off to have a tiny little dip in the luminance, because we're hopeless analog creatures when it comes to guessing what the luminance of something is. It's because we don't have a baseline except black. You close your eyes, that's black. But you go into a dark room, your eyes are going to iris up, right? And if there's a tiny little light, you're going to see it. Eventually, you're going to see that. So you're better off to have like a luminance error than you are to have a color error if it's green. So what is color space? I looked around and to try to find something that we can step to so that we can get to the CIE chart and make sense of the CIE chart. First off, color space is not a real physical space. Color space is, we use that term because it is 3D in nature. But we are looking at a 2D display. We're always looking at a 2D display, even in 3D mode, we're looking at a 2D display. So when we get back into talking about 3D color correction values, we're not talking about 3 dimensions of space. We're talking about 3 channels. Just think of it as 3 channels. What I wanted to show here in this one is how we have a unified space, and we have an axis, white, black through the very, very center, and then you've got your colors around the outside. This is one way of representing this, but it's very, very faulty in the fact that if you follow that logic, if you go out to green at the minus A, so the 100% green would have a 50% luminance value. That's all you could ever get. So that doesn't work. It's one way of looking at it, but that doesn't work. So people have seen this before, or something similar. We get into the cube idea. Is that just me, or is that a really parallelogram at the moment? This one, what I want you to pay attention to is the black-white axis going from the point, well, the point that you can see to the point that's at the back. And this one is just another representation, but you're starting to get an idea of, this is a little bit closer to what we see as humans, the response that our human eyes have. Let's face it, that's all we really care about when it comes to a display. Everybody's probably seen this. Most people have seen this. So this is that last chart, flattened out with a steamroller. But what you want to bear in mind is that the white axis, white to black axis, is that dot in the center. D65, a very common term. It was adopted many, many years ago, and I, for one, don't like it because it's not accurate. It's actually a thermal reading. And I'll give a very brief explanation. It's Kelvin. who was a scientist, I think he was a German scientist, and just came up with a theory that if you take a black box and you apply heat to it, eventually it starts to glow. And he applied degree values to that black box to describe the colors. And we, somewhere along the line, I guess it was SMPTE, somewhere along the line decided that the 6,500 degrees, or 6,500 Kelvin, is the color that we're going to use for white. That's for television. P3 is a different white, print is a different white, that's what we use for television. And more accurately, that is defined by the XY coordinates on this chart. X by Y. The X value is 312, the Y value is 329. Actually, that's 0.329, 0.312. That is a very exact value, and that actually corresponds to 6502, not 65. It's been abbreviated. Another thing we can see in here is the gamut. The gamut differences between UHD and high definition. You can see the 2020, the UHD is much larger. That's where we want to get to. That's a bit of a wild west at the moment. How many people here are actually starting to play with this sort of stuff? Yeah? Of course you are. You're selling lots of stuff, I suppose, yeah. It's still kind of a wild west, and the definitions are there, but a lot of the displays are kind of all over the map at the moment. So one of the initiatives that is coming forward now is called colored volume, where given a certain nit white point value, what is a display capable of in terms of the colored volume? This is going to be something that I think is going to be ratified fairly shortly, and it'll become a standard for that. Back to these objectives again. Now I'm going to start actually going through what we're looking for when we do each of these steps. So grayscale tracking will be first. How come that's out of the way? Sorry, we'll get something in the wrong spot there. Set up your hardware, set up a room lighting, probe placement, blah, blah, blah. I don't think we need to go into this anymore. Yeah. This is something that's fairly important, is provide yourself with a safety net for anybody that's a calibrator that is going into various facilities. Or even yourselves, if your display looks pretty good, write down all those values, because some things can go wrong. And it'd be nice to be able to at least get back to square one again and move forward. These are basically the values that you'll be looking for. And these consumer devices, they have so many funky menu names. Brightness, contrast, backlight, picture, they're all over the map, and you'll figure out what they do by adjusting them. You would take a look at the dynamic range. That is the capability of a display to accurately show all of the data that is in the standard. So in television, for instance, in television broadcast, we use 16 at black. I'm going to go 8-bit. So 16 is black, and you can go all the way up to 255. But we look at 235 as the 100 IRE units. I'm not using terms everybody understands, okay? You want to be able to see, though, on your display, you want to be able to see right up the top. You want to be able to see 255. The challenge of a lot of the consumer monitors to actually do that, to show anything beyond the 255. If you run these tests, this is sort of what you're going to see if the display is clipping. It may only be one channel. It may be all 3 channels. The only way I've been able to get consumer displays to open that up is to bring the contrast way down, which sadly, you lose light output, which is fine in a dark room. But if they have a lot of light in the room, then the display looks dull. So it becomes, as I say, these become trade-offs, these become compromises. Another one though, however, in some of these displays, especially on the HDMI inputs, is there's a setting for full or limited range. Full range should open it up all the way. So when you're looking at grayscale tracking, I wondered what this would look like on that display. Is it just me, or is it really green on the right?
It's green.
Right. Yeah, it kind of looks it to me from here, yeah. Grayscale tracking, that should be all the same shade of gray, given a change in the luminance value. This is just balancing off the R, G, and the B channels so that given the same input stimulus, they output the same amount. And that should follow a gamma curve as well. It's not a straight line. An interesting note here, just to tie in, is that light is not 100% red, 100% green, 100% blue. But that's what you'll see when you project, or when you send 100% white into a waveform monitor. That is jiggery-pokery, so that people can look at white and that it's all the same level for the three channels. And the colors can actually look at those and adjust the three gains so that they sit on top of one another, and then that should be 6,500 degrees, the white value you're looking for. But that's actually made up of 59% of green, 30% of red, and 11% of blue. And if people have ever really looked at that blue channel, it's really noisy. And it's really noisy because it's only 11% of white, and it's been pulled all the way up to match the biggest channel. So that's why we don't want a green error. I guess that's what that ties into. Because it's a large part of your picture. These charts here were taken from a calibration I did, so we'll follow it all the way through. This is my first pre-calibration grayscale read, and we can see that this graph has a large amount of red and not enough blue. What's kind of nice is the green's half decent. But what's not very pleasant to look at is that none of these lines are smooth lines. None of them are straight. And that's going to be a problem. It's not difficult for me to take the red down and the blue up so that they match at the 100% point. And if the display has a black level control, I can also work down here in the lower levels because there's interconnection. I know that if I bring this red down and I bring blue up, I'm going to have some effect here. Hopefully I've got a black control that I can correct that with. But once those are following the 100 line, I've still got these dips and doodles here to deal with. And not a lot of displays give you controls to adjust that. More and more are, I'm happy to say that. A lot of them are coming out with these 10 and 21 step grayscale adjustments in the display, so the controls are there if you can get at them. One problem I have seen is when the menu comes up, it affects what you're actually reading. So you have to look at it, bring the menu up, make an adjustment, take the menu away, take another reading. It's pretty painful. And also, some of these things haven't got very good filtering. I guess that's the problem. Because when you go in and you make those corrections, now your graphs look really, really good. Then you look at a picture and there's banding all over the place. So I avoid those if I can. So this picture would be kind of a yellowish color. Being as it's lacking blue, it will shift away from the blue vector, away from the blue. Remember the CIE chart? Blue was down in this corner, green was up at the top, the red was off to that side. So being minus blue means it went away from blue, and being plus red means it went towards red. So it would have shifted in towards yellow, essentially. Delta E2000, this is a reading. It's kind of a scorecard. It's a combination of luminance errors and chrominance errors for any one of these given steps. And it's kind of geared towards how noticeable is the error. On this scale, we try to be less than 3. Okay? I don't like to leave a display that's got a 3 error. I like it to be 2 or less. But in some cases, you just can't get there. In some cases, you can get a really good reading, but 1 or 2 spots are bad. There's not much you can do unless we can create a 1D LUT. And we'll get into that as we go along. So again, here's that chart, and you can see the white point has shifted towards the red. This is the CIE reading of that RGB chart. I know the RGB chart looked horrible, but that was just expanded out to exaggerate the errors. Also the effect here is of the white point being off, but we can also see that our secondaries are not in very good shape either. Green's not brilliant. Blue is in there. Red is actually quite good. But this display needs some adjustments in its color imagery for sure. And this is the same delta E looking at the luminance values of the colors. A lot of people don't realize that your red, green, blue, yellow, magenta, and cyan, it's not just a vector reading, there's also a luminance value. It's not just hue and saturation. They all have a value of luminance as well. And this is the gamma reading of that. Not exactly what we're targeting the 2.4, which is the yellow line. That's what I set my software up for. And what my software does is, instead of trying to calibrate on the curves, my software does a log over log, and it straightens it up to a straight line. So when I get the gamma to follow that line, I am at 2.4 gamma. Does that make sense? It's no longer a curve. Well, it is a curve, but it's represented as a straight line because that makes it a lot easier for us human beings. Okay, so this display is showing all the way to 255. I'm kind of surprised that it did that. This is 100% white, right here. A display that is limited to video, the rest of these chips coming all the way down to here would not be shown. They would be the same value as that 235, because that's all the display is going to put out. So if you're using this as a color correction suite or a very color critical place, you won't see data above 100 IRE. That would be a bad thing if you're working in a snow environment, if you're doing let's say a skiing video, or there's lots of clouds you're dealing with, or cars with glinting and white, it's just going to be flat. And black, how are we doing with black? We're not quite making the black, right? I mean, we're losing it right about here. So we got a little bit of black crush that we can see, but what's very, very important to bear in mind is that's in this lighting. If we bring the lights down, there's a chance we'll see more chips. Probably we'll see more chips, but I don't know that we'll see them all. The black, the lighting in the room really affects your appreciation of the black. And decoders, a lot of the decoders are fine in digital displays. I've seen a few that are really wonked out. And if it's really bad, is this showing red? No, that's interesting because this chart actually is leaking red into this, so it shows a bad decoder setup. There's not very much that you can actually do in the new digital displays to correct this. You can actually get into the hue and or chroma saturation. Some of them are locked off if you're in a digital format. Some of them you still have control over. And make a tweak on it, but it's a little bit scary when the decoder is wrong on their display. The manufacturer made it, so it should be correct for that display. So now we've adjusted the red, green, and blue controls on that display. We've got it flattened out. The channels are sort of following each other, but you see those humps and bumps and dips. So if we put up a 21-step reverse grayscale, where it's black to white on the top and white to black on the bottom, you will be able to see the various colors. You'll see it from, say, 10 to 30 will be plus red. It'll be a tiny bit on the warm side. Pretty good at about 35. 40, I'm not sure what you'd see there, but from about 45, that's my angle, 40 to 70, it's plus green. And there's an awful lot of skin tone in that area. Leaving that display like that, you might have problems with skin tones later on. So you want to pull that back down again. So the compromise there would be to pull the green down a little bit. I would sacrifice it at the top end rather than at the bottom end because of the luminance. 100 IRE has got a lot of white component in it. So a small green area there, it's a small amount of saturation against 100% white. Whereas that same error in black could be 10 times that error, that perception. So the post grayscale, not too bad. We've got everything south of 3, which is our error. But I think a little bit more tweaking would solve that. And the result is it has fixed an awful lot of things here. We've got the white point, and what you can't actually see is behind that white dot, there's actually a black dot. So the black to the white is tracking in a nice, fairly straight line. It only took 2 readings. In this case, there's only 2 readings there. We've got some, well, the primaries and the secondaries, they're all looking pretty good. What's really important when you're working with a color management system and you're playing with the primaries and the secondaries is you want to have the luminance value of your primaries. That's the most important part. And then when you get to the secondaries, it's the hue and saturation of the secondaries that you want to work on. If you have to make compromises, those are the targets to go for and compromise the other. So we've talked about this here. The gamma correction is better, but it's not a straight line. But it's certainly averaging 1.94. That's still pretty bad, actually. Post-cal data, this is probably the most important part of my reports. Those things that you just saw, those charts that you saw, are all part of a report that I would give to my client. But the pre-cal data is important, but this post-cal data, this is where the rubber really hits the road. This is the meat and potatoes. This is something a customer can look at and say, okay, I can see at the 40 IRE units, my CIE targets are 313 and 329, but my actual, which is the top two rows, is 312, 328. That's really very, very close. My delta E error is only 0.711. This display actually is looking pretty good compared to where it was at 40, it was 6.5. A big difference, a big improvement has been done on this. But like I said, there's no perfect display, and this is certainly not one. Then the sanity check. I was mentioning this briefly with Bert, is you folks, except unless you work for GSE Lab or something, you don't sell test signals, you sell content. So you can go through and you can use these tests, and you can get these charts, and everything looks kind of hunky-dory, but you might need to check it against the real world. And I tell colorists that are asking, you know, like, how do you know a display's off? And I tell colorists, get some challenging content, something that's got a lot of white in it, a lot of black in it, but there's lots of detail in those whites and those blacks. Take those pictures, get them, if they can, get them as TIFFs, something that's uncompressed, and carry them around on a USB stick, and, you know, load it into your DaVinci or whatever your color system is, and put it on your display, and take a look at it. Especially, like, get used to what a calibrated display looks like, so that when you go to another display, you'll be able to tell. You know, you know that I don't know what maybe this girl's hair is a little bit more on the red tint, but on this display it's not, and so you know that there's something wrong here. That's the best suggestion I can give for anybody that just wants to know, how can I just look at my display and tell whether or not it needs something? You need to have a number of test signals that you know, and you put it up and you look at it, and does it look right or does it look wrong? Trust your eyes. If it looks a bit wonky, even though you might not be able to define why it looks wonky, if it looks wonky, it probably is wonky, as long as the viewing environment is not drastically different. Clipping in the whites. I'd say clipping in the blacks too. There should be detail under that trunk. There's a bit of clipping. Those trees should have details in it. They're a little bit flattened out. So you've gone through what we just talked about, was color correcting display, calibrating display, sorry, using only the local controls that are on the display. That's the black controls, the red controls, the red, green, blue. Sometimes they have gamma selections. They have color mode selections that you can play with to try to better target that white point before you make adjustments. But sometimes it's just not enough. So now you need to call in some extra help. And that would be in the form of a color management system, which essentially are LUTs. Yeah, an important little side note here is if you've made color, if you've created a display LUT to compensate for your display's failings, so your display looks correct now, but you've actually altered the data to make the display look right. I know it seems really weird, but it'll make sense later on. Never use that pipeline to record your data to send it someplace else, because you're messing up your data in order to make your display look right. So you don't want to mess up that data and give it to somebody else, because it's not truly what your data is. You put it through a transforming device so that your display looks right. So now your display actually is showing you what your data is, but the data had to be altered to force the display to look right. So never use that output as a data output. So what are LUTs? Stands for lookup table. Basically, you have your data coming in, and you have something happening to it, and it goes back out. If the LUT is doing anything, what comes out is not what went in, and that's why you don't want to record that data. What we're doing in this case for a 1D LUT is we're going to correct that straight line for white and black. We want it to be a straight line, and we want it to be all the same color temperature every step of the way. That's the easy part. You take a look at the RGB readings. I think I got it. I'll finish up with the 3D LUTs here. With a 3D LUT, you've got that 3D space right? We talked about what that is. We've got the 3 channels. Every single binary value for red, green, and blue interacts with the other channels in order to make your colors. It's not possible, even in an 8-bit system, to read all of those values because there's 16 million of them. And to read all of those values in order to create a corrective LUT for every value, it's months of work, really. I mean, I don't know, I didn't do the work, but I know it's at least a couple of weeks of just trying to read them. So what we do is we make something that's, we take representative samples. And it's important to take a lot around the skin tone area. And then the software analyzes where it should be, and it creates a corrective value for that point. But then it looks at the next point that surrounds it, and it has to do interpolation. So there's a lot of jiggery-pokery math going on, but it's not going to be perfect, but it will be better. You can just imagine, like in a 10-bit system, you've got a billion colors. It's just, yeah, you can't do it. What you have to do in order to build a LUT is the first step is you want to optimize that display using the local controls. You don't want to force the LUT to do any more work than it has to. The display itself should be in its optimum position first. And then after this LUT is created and loaded, don't touch the display because then you invalidate the LUT. Okay, then you have to profile the display. The profile of the display is to take all of those samples and record what happened. What did your probe say the value of the red, green, and blue channels were, given all of the test criteria that you sent it? Record all those. We know, because we generated those test signals, what the value should be. So now we've got to create a LUT so that the display now reads back what that data is. But we know without the LUT, it's not correct. So the LUT is going to change the data to force the display to show the value that we want. And that's about the briefest explanation I can give. Then after that profile is made, and if I'm going to do a 3D profile, I'll set it up for at least 2 hours worth of samples. And that's usually runs somewhere around 2,300 samples. It'll take in a couple of hours. But that's such a small percentage of the color space that we're talking about. But it's amazing how much more accurate things can become as a result of that. The problem with that, as we saw, the channels don't, if red's not in the right spot or green's not in the right spot, it doesn't get there from black in a straight line. It wobbles all over the place. So the best thing you can do is take a number of samples and try to hit a spot where, okay, it's gone plus here, a bit too much plus here, and we can make a correction. And we'll assume that it was kind of smooth up to that point, and we'll bring it back down. Then after it's created and you load it, you got to check it. Because once in a while, a hiccup happens. And when a hiccup happens in a LUT, it's really ugly. I mean, your picture is completely useless, really. And that can just be one error someplace where it just sent something off. And depends on the bit error, you know, but if it's around a middle bit error, that's a very significant error. And the software doesn't know that that's not right. It's going to make a correction based on what it got, what it was fed. So what goes in is what it has to use in order to create a LUT. So more samples means you have less interpolation, but more samples means a lot longer. So what's it worth for? After a 1D LUT, and we've loaded this LUT now into the display, you can see the gamma correction is not bad. We got a little bit of a hump on the very, very top. That's fairly typical of large displays. Once they get really up very close to the peak white, they don't put out as much at 90 and 80 as it actually should. I don't know if that's the green factor, you know, the Energy Star that they're doing, or they're cheaping out on power supplies. I'm not quite sure exactly what that's, probably a combination of a couple of things. But a lot of the larger displays will give you very, very poor performance in the whites in terms of the gamma, in terms of the curve, the amount of output you should get based on taking a reading at 100, taking a reading at black. You can calculate what 90 should be and what 80 should be, and quite often it's not right. So if you want to have a little bit more accurate reading on a big display, you can help yourself. There's a good hint guide. Is use a small pattern. Don't use a full pattern display. It's too challenging for the big displays. Use a smaller pattern. It helps. On an LCD, like a computer monitor, by all means, use the full one. This is a really small subset sample that you would use on a 3D, creating a 3D line. This is just the red channel, just the green channel, just the blue channel. But there's all those other colors in between that haven't been touched yet. So you've got to take a lot of samples to make it accurate. We've seen that before. And then finally, we have a post verification on here. This is not the same display as those other graphs being from. This is actually a computer display. And I created a 1D and a 3D corrective LUT. The LUT was loaded into the graphics card of the computer itself, which is a very, very inexpensive way of creating a LUT. On something like this projector, for instance, I mean, you wouldn't want to spend the money on this, but let's say you had to get this correct, then you'd have to buy an external processor. There's a number of them out there, and they range anywhere from $700 and up. And that is where the magic will happen. You still have to calibrate that display as best you can locally, and then you have to create these 1D and these 3D LUTs and put it into this external box. But with, in the case of computer generation, I work with a lot of animation houses, special effects houses, and they've got a lot of, they'll have a number of people that are in charge of lighting and textures and what have you. And they have to have a fairly accurate display, but it's a PC display. And I will load a corrective LUT into their graphics card. This does not work with Blackmagic breakout boxes or Azure breakout boxes, because that's not part of the computer system itself. That's an external box. But this works now. The software, in particular CalMet, which generated this graphic here, works in all Microsoft Windows, and it works with the Macintosh OS, but it does not service the Linux environment, which of course a lot of computer generation guys are working with. So for that, there's other applications. I'll tell you, it's Argyle is one that I've used quite successfully in a number of facilities. And Argyle, though, is a command line interface, which is great for the geeks and the propeller heads, but I need the graphics. So you also, once you get Argyle loaded onto your Linux box, you also want to get DisplayCal GUI. DisplayCal is a front end. Somebody was so nice to write a graphics front end for DisplayCal, or for Argyle. And you have to go through it, and you have to tell it what your white point is going to be, how bright you want it to be, what your gamma curve is going to be, your color space, and then it'll go off, and it will basically do what this software does. It reads it, generates calibration signals using the graphics card. The graphics card becomes the test pattern generator, feeds the display, reads it, comes back into the software, and it creates the corrective LUT for your display. There's a number of places I've used this in, and in fact I've even been hired to establish a color pipeline for them and then teach their staff how to do it themselves. And it's worked quite successfully when it comes to us. So after you've done your calibration, the reports are quite important. I think that validates what you've done. If you're doing it for yourself, I still think it's a very good idea to generate these reports and keep them as a tracking of the performance of any particular display over a period of time. And you may notice that, well, you know what, after 4 months, this particular display consistently lacks blue. And if that's the case, I'm going to almost guarantee you it's a probably cold cathode backlight, fluorescent backlight. But then you can start to see, well, you know, after 6 months, these displays, which might be LED backlights, are quite stable. So I'll check them maybe in 8 months. But you can also see when something really starts to happen with your display. And you can get rid of it before you've invested a lot of time color correcting something or generating animation on a display that's bad. And you have to go back and redo that work. Because the cost of replacing a PC display is a lot less than having to redo a job. This is an example of the reports that I give. It shows the technology that I use, the meters I use, the name of the display itself, my pre-calibration readings. In this particular case, it was all just default. I did not change the picture mode because the client had already selected movie, and that was the closest one for the standard that they wanted, which which was Rec 709 and with a DT 1886 curve. I also record my post-calibration settings because we all know that once in a while gremlins come in at night and they get reset on something and it's lost. At least this way they can get back into pretty good shape. If, in this particular case, this display had an onboard color management system in it, and more displays are doing this, not just for the 1D left with grayscale, but they're also allowing me to go into the red, green, blue, cyan, yellow, cyan, magenta, and the other, and adjust the hue, saturation, and luminance of each of those. So you can theoretically get those values perfect, but you want to go back and look at some content after that, because I still don't trust these things for not creating very obscure banding. Look at a radiated sky or something like that, and if you see banding and you turn off that CMS, I bet you turn the CMS off, it will be gone. So again, it becomes a challenge, it becomes a trade-off. And in this particular case, I took pictures with my phone of all of those menus because I don't have those menus in this software, but for the CMS I took those, and I just added it to the report later on, so they have everything. Full service guy. You saw these charts, but this is how it comes in the report. It puts them side by side. It's nice that the client can see this and say, well, he did something. Again, you've seen all these, so I'm not going to go through them again. The calibration data, and I'm going to leave you with this one. If you guys are professionals and you're doing professional production and if you're not calibrating your equipment, then it's not really professional, so call me. And that's it. If there's any questions, I'll take